we have earlier discussed about the concepts of heat and work, and it is important that we go through the exercise of solving some problems related to the concepts of heat and work. So, we start with a very simple problem which is given here. As we have done for our previous problems, we will do it in the same way. We will go through the problem description first, and then we will go to the board, draw a schematic of the problem, note down the given data and try to solve the problem. So, you have a piston cylinder arrangement. It initially contains air at 150 kilopascal and 400 degree centigrade. The setup is allowed to cool to ambient temperature of 20 degree centigrade. The question is the piston resting on the stops in the final state? So, you can see that physically what is going to happen is, if heat is transferred from the system, which is air in this case, the piston will start going down. So, in the process it may hit the stops or not. Question is, at 20 degree centigrade the final temperature, will it hit the stops? What is the final pressure and what is the specific work done, that means work done per unit mass by air during the process. So, let me first draw a schematic of this problem and see what is the given data, and then we will solve the problem accordingly. So, this is the air which is our system. So, for this system state 1 is given as P1 is equal to 150 kilopascal and T1 is 400 degree centigrade. State 2 is T2 is equal to 20 degree centigrade, and this volume, this is, so this length is 1 meter and this length is 1 meter. So, let us try to address the first question, that is whether the piston will hit the stops or not. Now, first of all, what kind of substance is this air, that we have to figure out. See, in thermodynamics there are certain substances which are sort of phase changing substances, and you require to read the property table to evaluate their properties. In certain cases the substance can be idealized as an ideal gas, and normally even if it is a real gas at very high temperature or very low pressure or a combination of these two, you can treat the ideal gas, the real gas as an ideal gas. So, here At least at state 1 the temperature is quite high, pressure is close to atmosphere, 1 atmosphere is roughly 100 kilopascal. So, in that respect treating this as an ideal gas will not be a very bad assumption. So, at state 2 the question is that will it hit the stops at state 2. So, let us assume that it hits the stops. If it hits the stops, then in that case V2 is V1 by 2. Why? Initial height is 1 meter plus 1 meter, when it comes down and hits the stops the height is 1 meter. So, area of cross section remaining the same, V2 becomes V1 by 2. Okay. So, then you can write for ideal gas remember that when you are using this ideal gas equation, this T1 and T2 are absolute temperature. So, this is 400 plus 273.15 Kelvin and this is 20 plus 273.15 Kelvin. V2 is V1 by 2, P1 is 150 kilopascal. So, from here you can calculate what is P2. So, if you calculate, P2 will come out to be 130.7 kilopascal. This is less than P1. So, from here what can you conclude? See, if this is moving, this piston is moving in a quasi equilibrium process, because the resistance pressure does not change, the inside pressure will not change until and unless it encounters the stops. When it encounters the stops, it wants to go down, but the stops is preventing it from going further. So, the very fact that the pressure has come down to 130.7 kilopascal and this is because of continuous heat rejection, it signifies the fact that it has already hit the stops, because if it does not hit the stop or just it has just hit the stops, the pressure will still remain 150 kilopascal. Because it has not remained as 150 kilopascal and it is less than this one, that means it has hit the stops. So, the question, the answer to the first question is the piston against the stops, resting on the stops in the final state? The answer is yes, and this is the pressure at state 2. Then now what is the specific work done by air during the process? So, for any problem where work done is involved, it is very convenient if we can draw the PV diagram, because PV diagram gives us a physical insight of how pressure is changing with volume, and then integral of PdV will give the work done for the simple compressible pure substance. So, to do that, what we will do is we will consider the state 1, this is P1 comma V1. From state 1 what is happening? The piston is coming down, so its volume is decreasing at constant pressure of 150 kilopascal till it encounters the stops. So, volume is reducing, so it comes to a state 2A, where still the pressure is P1 and volume is V stop. Then it cannot decrease its volume anymore, but because of continuous heat rejection the pressure is decreasing. This P2 is 130.7 kilopascal. Okay. So, what is the work done? This much. So, this is integral PdV from 1 to 2A plus integral PdV from 2A to 2. This part is 0 because it is a constant volume process. So, and during this part the pressure is constant at P1. So, it is P1 into V2A minus V1, and what is V2A? This is same as V2, which is V1 by 2. Okay. So, you can substitute the values and get what is the work done. So, you can find out the work done only per unit mass here, and that is what is expected. The question is what is the specific work done by the air during the process. Okay. So, in this case if m is the mass of the air, then this is m. So, V2A is first of all V1 by 2, then you can write P1 V1 into half minus 1, that is minus half, and P1 V1 is mRT1 minus mRT1 by 2. This T1 is again absolute temperature. What is this R? This is specific gas constant, not universal gas constant. This is universal constant divided by the molecular weight. So, this is per unit mass. For example, for air it is 0.287 kilojoule per kg Kelvin, right. So, if you do that, this comes out to be, the answer to this is minus 96.6. per kg if you take m as 1 kg. Okay. So, in this case the answer is minus, the reason is that there is work associated, which is work input, so that the system is getting compressed. If work leaves the system, what is the sign convention? If work leaves the system, it is positive. If work gets into the system, which allows the system to get compressed, then that work is negative work, and that is why it is minus in this case. Okay. So, let us work out another problem. So, problem 2.2. there is a refrigerant R22, this kind of name are with certain numbers and in some cases with certain letters. This combination is normally for refrigerants. So there is a refrigerant which is contained in a piston cylinder as shown in the figure, where the volume is 11 liter when the piston hits the stops. So if it hits the stops, the volume is 11 liter, the initial state is minus 30 degrees centigrade and 150 kilopascal with a volume of 10 liter. The system is brought to indoors and warms up to 15 degrees centigrade. So from minus 30 degrees centigrade heat is transferred so that it comes to 15 degrees centigrade. So when heat is transferred it will expand and the question is, will it hit the stops or not, and what is the work done by the R22 during the process. So just like the previous problem, let us draw this in the form of a PV diagram. Before that, let us make a schematic of the problem. So V stops is equal to 11 liter. 11 liter is 11 into 10 to the power minus 3 meter cube. Then state 1, T1 is minus 30 degrees centigrade and P1 is 150 kilopascal. And V1 is 10 liter. So for such a substance, from this information what additional thing that you can calculate is what is the mass of R22. So you have the system here, so in this system at state 1, so you have two independent properties. So not ideal gas, by using the property, see this is where I want to emphasize that from school level when you come to the college level, this is where in most of the cases you have a confusion. In school level almost all properties related to thermodynamics are corresponding to ideal gases. So very frequently you are using ideal gas relationships. So for this you are tempted to write say P1 V1 is equal to MRT1, something like that. So the question is that when you have this P1 V1 is equal to MRT1, can you use that formula here? The answer is no. This is a very typical phase changing substance, and in that scenario you cannot really approximate it as an ideal gas. That will be a very wrong approximation. In reality no substance is an ideal gas, but for certain substances approximation as an ideal gas is not a bad approximation. In this case the approximation is a bad approximation. So, from table of R22 you can find out what is V1 from T1 and P1, and then the mass which does not change from state 1 to state 2 is simply V1 by small v1. This is volume per total volume, this is volume per unit mass. So, that is the mass of the system. So, now let us look into the thermodynamic process what is asked. So, heat is transferred and the system is heated. So, if it heats the stops, we do not know whether it has heat the stops. If it heats the stops, then what is the specific volume at state 2? Specific volume at state 2 is V stops by M, that M you get from here. So, now from V stops by M, that is I do not have the data, but you can calculate what is the pressure at state 2. How do you calculate what is the pressure at state 2? There is some additional data which is given. So, state 2, remember always try to follow these problems in this way. So, to identify a state point for a simple compressible pure substance, you require two independent intensive properties. So, one property is this one, the other property is T2 is equal to 15 degrees centigrade. Okay. So, this is still a hypothetical state, because this state is true if it hits the stops. If this state, so we have to verify whether it hits the stops or not. This is a very important part of the problem, and this is where thermodynamics is so challenging. If the verification does not show that it hits the stops, then this state remains hypothetical. If the verification shows that it hits the stops, then this state is real. So, whether this state is real or hypothetical, that needs to be worked out from the problem data itself. So, unlike many other subjects where changing the data does not change the method of solving the problem, in thermodynamics changing the data itself may change the method of solving the problem, and that makes this a very unique subject where just by a structured way of solving problems you cannot really make a grasp on the problems. So, you have T2 as 15 degrees centigrade, V2 as this combination V2 T2, this combination from R22 table will give you what? From R22 table, this will give you what is P2. Okay. So, once you have got what is P2, then what you do with this? Let us say that we have got P2 as 164.7 kilopascal. This is what actually you will get if you look into the table. So, I have jotted down this data because the problem solving further depends on this data. How it further depends on this data? This is greater than P1, right. Had this been less than P1, less than P1 is not what is expected because heat is transferred to it and it is moving. So, how its pressure can fall down below P1, but incidentally its pressure could have remained same as P1, that is possible. Had its pressure remained same as P1, then that means it might not have hit the stops, you are not sure, or in the limiting case it may just have reached the stops. However, when it is greater than P1, that means it has hit the stops and then the pressure is going up, right. So, that means it has hit the stops. So, once it has hit the stops, then what will happen? Its volume cannot change anymore, but its pressure will build up because heat is transferred to it from the room, the room is hot room, heat is transferred to it, it wants to go up, but stops are preventing it from going further up. So, its pressure will build up inside. So, the PV diagram will look something like this. 1 to 2A is, this is basically stop, and then from here to state 2 the pressure will rise. So, you have to find out what is the work done in this process. So, what is the work done? Just like the previous problem, so this part is 0 and this is 1 into V2A minus V1, and V2A is same as V2. And by expressing this in terms of the specific volume, you can write in terms of specific volume, and this comes out to be 0.15 kilojoule. The final pressure does not matter, right. So, if you cannot draw this PV diagram correctly, I have seen some students making mistakes here. They will just have 0.1 and 0.2 and they will write the work done as half of P1 plus P2 into V2 minus V1, because they will draw the PV diagram incorrectly as this. So, the PV diagram is not like this, it is this step plus this step, one constant pressure, another constant volume. Thank you so much. We will continue with more problems in the next lecture.